Hey, Miss Penna, have you ever seen Pascal's triangle before?
Yes, I think you have it right over here, but I've noticed that there's this triangle. I'm not really sure what that is. Can you explain?
Well, I can try. See, the other day we were talking about making a pizza, and we had five toppings to choose from. And if we went through the cases of choosing like no toppings and then one topping and so on, we found out that if we take all those cases and add them up, we got all the possibilities, which was 32, and we saw that that was like 2 to the 5 toppings in total. And then, if you look at the numbers, 1, 5, 10, 10, 5, 1, those were all the different possibilities for, choosing 5 toppings, let's say. We could only do that one way, whereas if we chose only 2 toppings, there was 10 ways of doing that. And lo and behold, 1, 5, 10, 10, 5, 1 were the numbers in the fifth row of Pascal's triangle.
Oh, okay, Mr. Langford. So I see that combinations are directly related to Pascal's triangle. First, if we take a look at the n value, we notice that that's related to the rows for Pascal's triangle. And then if we take a look at the r values, they're specifically related to the placement in our triangle. So the first term has an r value of 0, then the second term will have an r value of 1, and depending on your n value, you're going to continue until you get to all of your n values, which is exactly why this is related to the subsets, because we were considering all the different cases. So you have 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. So all the possible subsets of 5 items.
Well, that's pretty cool. So if I wanted to know like what the numbers were in like the 100th row of Pascal's triangle, I wouldn't have to write out the whole triangle, would I? I could just say, well, the numbers start with 100 choose 0 and go all the way across 100 choose 1 and then 100 choose 2 until I get to the other end where it's 100 choose 100. Now that's a lot of numbers, but I could do it.
Exactly.
Okay, well that's pretty interesting. But I'm looking down the page and I see some pretty scary algebra. I don't think this looks like very much fun.
Well, actually, Pascal's triangle makes all of this algebra so much easier. There's a relationship between Pascal's triangle and the coefficients when you expand a binomial. Take a moment now, pause the video, and expand a plus b to the power of 3 and see if you can find that relationship.
Hey, I think I see what's going on here. If I look at the coefficient, which means the number in front of the variable in each term of a plus b to the 3, I see the numbers from the third row of Pascal's triangle. So we have 1a cubed, and then 3a squared b, 3ab squared, and then 1b cubed. And those coefficients, 1, 3, 3, 1, are in row 3. And 3 is the exponent that we were using in our expansion. That's pretty cool.
It is really cool.
So I think I see where those coefficient numbers come from, but how do I know what exponents are supposed to be on A and B when I go along?
Well, the exponents are actually just your r value. First, take your b in our case. So here will be b. And you're going to put it to your first r value. So in this case, it's b to the power of 0, which is also just 1, which is why it isn't written there. And then in the second one, it would be b to the power of 1. And then we go b to the power of 2 and b to the power of 3. And if we take a look at our r values here, it goes 0, 1, 2, 3. And then our a values are doing the exact same thing. Sorry, not a values, our a exponents. They're just going down. So we go 3, 2, 1, and then in here, that's like writing a to the power of 0.
Oh, okay, so I don't have to memorize anything. I just have to remember to count down for the first variable and up for the second variable from n in the n down to 0 for a and 0 up to n for b.
Exactly.
That's okay, so if I follow the patterns, I should be able to expand a plus b to the exponent 4 without really multiplying anything, just using the pattern from Pascal's triangle and how we counted down for the exponents and write out the expansion of a plus b to the 4. Pretty easy, eh?
I think you can, and I bet you all of you can. So right now, pause the video and see if you can complete the expansion of a plus b to the power of 4 and a plus b to the power of 5 just using Pascal's triangle.
Okay, so for a plus b to the 4, we have explicitly shown that each term contains a coefficient from Pascal's triangle. So in the first term we have 1, then a to the 4, b to the 0, plus 4, a cubed b to the 1, and so on down the line. So if we understand that coefficients of 1 don't need to be included, and exponents of 0 don't either because they're 1, then we can just write for a plus b to the 5, a to the 5 for the first term, plus 5a to the 4b, plus 10a cubed b squared, and so on. And you know what's neat there, Miss Pennant, is that I can see that the exponents for each term always add up to the n number. That's a good way of making sure I don't have a mistake.
That is a really good way of making sure you don't have a mistake. That's awesome. So in general, the binomial theorem gives us the expansion of a plus b to the power of n. And we can write this down as a plus b to the power of n is equal to, our first coefficient is always n choose 0, and then of course we start our exponents for our a's with n, and we go down until we get to 0, and we start our exponents for our b's at 0, and we go up until we get to n. Sorry about my penmanship, but that should be an n. And the coefficients of the form n choose r, which of course can also be written as n choose r, are called binomial coefficients.
So when we talk about the general term of a binomial expansion, what we mean is that any term along the list of all the possible terms in an expansion of a plus b to the n, in general, can be found by taking n choose r and multiplying by a to the n minus r and then b to the r. And so depending on the size of n and r, we could have, only a few terms in an expansion, or if we have a n value of 12, we would have 13 terms in the expansion, which could be pretty complicated if you tried to multiply it out, 2 binomials at a time until you got to all 13 terms. So what we can use now is the patterns in Pascal's triangle and our knowledge of combinations, and see if we can expand 2x plus 3 to the 4, and then we want to try and find the fourth term only in the expansion of x squared minus 1/2 to the power of 8. See if you can do those.
Try these two examples for next class, and we will take them up in class, as well as continue our discussion with Pascal and look at his identity.